All right, thank you. So we're moving on to the NEAT NSUF topics 1.1a and b. So two separate calls. In this area, Keith Leonard is the technical point of contact. So in this area, it's looked at both in terms of the NSUF resources required and ability to support the call, as well as a technical review by the program, and because the program would support the research that's associated with the use of the NSUF facilities. So you really get looked at from both sides on these calls. So I'll skip over the overview. I already covered the materials degradation overview as well, so I'll skip to the first technical slide and hand it over to Keith Leonard.
Okay, so for the NEET call, there's two of them, 1.1a and 1.1b. They are both looking at neutron irradiated properties of materials. This first one is part of, is in collaboration, or is in conjunction with the LWS Advanced Replacement Materials project, and which is a collaborative effort with EPRI's Advanced Radiation Resistant Materials project. And the aim is to develop new advanced alloys for use in LWR applications that would provide greater margins of performance above currently used materials. So in the on the right there is some of the alloys of interest. So there's nickel-based alloys and stainless steels. So nickel-based alloys are comparison to X750, and steels are generally in comparison to 16L. So some of the alloys of interest are listed. I'd like to point out that based on kind of evaluation of some of the data, I'm going to be less likely to favor steels that are research that is involving H29. There doesn't seem to be as great of a benefit at the lower radiation temperatures above the standard 304 and 316L series of materials. So the program that this is based off of, the ARR program, has been involved for some time looking at mechanical and fracture toughness properties of as-received materials, looking at microstructural stability under proton-radiated conditions and high-temperature oxidation testing. But we want to move things forward and look at neutron radiation effects. So that includes long-term effects such as swelling, solid segregation, precipitate changes, also mechanical property changes. Radiation, fracture toughness changes associated with radiation damage. And also, also important is radiation-assisted stress corrosion cracking issues under these conditions. So while there's a lot of information on some of the materials for radiated properties, a lot of these properties are based off of fusion program or advanced test reactor programs. They're really looking at radiation temperatures much higher than LWR needs. So while there may be a fairly large database in some areas, that database may not be necessarily representative of LWR conditions. Okay, Rich, so the next area is also kind of a follow-on to current LWRS efforts, and this is addressing the long-term performance of cast austenitic stainless steels. So this addresses a DOE NRC evaluation in terms of looking at cast austenitic stainless steels or cast alloys for 60 years and beyond. And the aim is to build, to systematically build a scientific knowledge base within a limited time frame. So much of the work that's currently going on is looking at thermal aging effects on these steels. So what we're seeing on these materials is that thermal aging effects are really quite heavily dependent on the starting microstructure. So how much, as you may be aware, the microstructure is a duplex structure because of the cast of delta and austenite grains. So depending on how much delta ferrite is present in the material is going to really dictate pretty significantly on or impact the properties in terms of long-term aging. One of the areas that's of particular interest to us is how radiation effects play into those synergistic effects with thermal aging, and that's what this proposal is interested in. So it's interested in involving a combined approach of modeling and experimental approach to evaluate the microstructure-driven mechanical property changes. And so for both subject areas, there's been a lot of recent development, both in terms of testing techniques and proven small-scale test specimen techniques that can be utilized, and they have been utilized in the NSUF supported national labs. So there's resources out there available for this type of work. And that's about it for this. So if there's any questions on 1.1A or 1.1B, I'd be happy to answer.
We don't have any questions on the NSUF areas yet, but we do have a question for Curtis on the RC8 and 9 areas. Curtis, what about dynamic models connected to RELAP 5 3D platforms?
Say that again.
Are dynamic models connected to RELAP 5 3D platforms of interest?
Probably not. The only information I think, if a static model used, say, a RELAP 5 calculation, the results of that may be used to help, say, benchmark a RELAP 7 calculation. And so we can leverage that information from the static model if it exists.
Would you be interested in, this question is for Keith now. In NSUF 1.1A, would you be interested in grade 91 steel?
Yes.
Are you interested in sequential radiation and thermal effect studies or parallel radiation and thermal aging effects of CAS, CASS?
Yes, because it's going to definitely be a challenge to address this issue of synergistic effects. So the approach is going to be has been an area that has been debated by a number of people back and forth quite a bit. So looking at so I'm fairly open right now to different techniques or methods to approach this issue. But there's going to have to be some scrutiny and justification as to the approaches that are provided.